Hello, this is part 2 of the video on fraction numbers and the decimal representation. In part 1, we're going to review the process of long division of a particular case, which is fraction number 1 over 7. And we went through the process and found out that it is actually a repeating pattern of 0.142857. Now, and we're asking the question, is this, kind of true for any other number? And we say that the answer is yes. So today we're going to examine a generic case of a fraction number p over q, where p and q are integers, and then we're going to see why is either terminating decimal or repeating decimal, for that fraction numbers. All right. So this is part 2 of the topic. Review the remainder from the non-division process. For example, when q equals 7, we know that if the divisor is 7, then each time when we do the non-division, the remainder can only be 0, 1, 2, 3, 4, 5, 6. So up to 6. Now, when we do 1 over 7, this is what we got, right? On the top, we got, of course, we ignore 0 here at the beginning. 1, 4, 2, 8, 5, 7, and then repeating. And the remainder, at each step is 3, 2, 6, 4, 5, 1, and then repeating. Notice that there's no 0 here, because if there's 0, then the process will terminate. Alright, so it's actually, in this case, there are only 6 cases, and we have all 3 numbers here, or 6 numbers here. Now, in general, for a fraction p over q, when we do long division, we're going to have remainder, 0, 1, and then up to q minus 1. Alright, of course, in this case, q is always positive. If a remainder is 0, that means that the division process is going to stop, and it also means that the number of decimal digits is finite. Alright, so it's terminating. Now, example would be in this case. Alright, there's no more. That's it. Alright, so but what happens if there's no 0 remainder? What do we get? Alright, so in that case, because it's never 0, then it means it never stops, it's never terminating, right? So the process never stops. And the remainder can only be 1, 2, up to q minus 1. So there's no 0 here. So we have a total q minus 1 possibilities. Now the question here is, will the remainder sequence repeat itself? Alright, so if we understand the long division process, we realize that the remainder pretty much determines the process. Right? For example, if I have a remainder 1, next time if I got the remainder 1 again, then from that point on, whatever the steps is going to be identical from my current situation where I have remainder 1. Alright, so back to the example of 1 over 7, we know that initially we have 1 here, as long as the remainder is 1, 3, 2, 6, 4, 5, and 1. When the remainder shows up again, the process is going to repeat this sequence. And now we understand, there is a pigeonhole principle. If n times n items are put into m containers, where n is greater than m, then at least one container must contain more than one item. Basically, the number of items is more than the containers. So, each one and contain 1, then the total number would be less than n. All right. So this is very intuitive, right? So in that case, this is a picture just show that I only have 9 holes, and then but I have 10 pigeons, so at least one has to have 2 pigeons, right? Now, when P and Q, we call it rational number, and we claim that every rational number is either a terminating sequence or repeating decimal. So why is the case? When you think about it, right, if 0 is terminating, if it's non-zero, then the length of a repeating is at the most q minus 1, right? Because we only have q minus 1 numbers, but if you have infinite many sequences, then at least one number has to repeat, right? If that number repeats, then you know that the sequence is going to repeat. This is kind of an infinite, running sequence, but it has a pattern that is going to repeat, and the pattern length is going to be at the most q minus 1, right? Because you cannot have more than a q minus 1 sequence number where the number never repeats in the sequence. So for example, 1/7, here the length is 6, all right? So 7 minus 1. Of course, sometimes it may not be exactly q minus 1. It could be maybe a factor of q minus 1, as we can see later. Now let's again to think about what is the process of long division for a number divided by 7. We already studied 1/7, but what about 2/7 or 3/7? All right. So keep in mind that the remainder pretty much decides the future. All right. If the remainder is 3, the sequence of the remainder is going to be this. All right. And each remainder is going to decide the next quotient, what number you're going to put in the result. Okay. If the 3 is the next is the remainder, then the next quotient would be 4. If it's 2, would be 2. If it's 6, would be 8. So for example, from this diagram we can say it's 1/7 because 1 as a remainder, the next quotient would be 1, the next remainder is going to be 3, the next quotient would be 4. So 1/7 is going to be 1, 4, and then come to 2, 8, 5, 7. Okay, let's try that. So 1/7, I have some program to calculate what is the decimal representation here. All right, so this is correct. So what about 2? All right, as we know that for the 2, if the remainder is 2, the quotient is 2, and then the sequence is going to be running from here fixed, because it never changes the order. Now, of course, this will not change in the order. All right, so it's going to be 2, 8, 5, 7, 1, 4, right, and then repeating 2, 8. So let's try that. Okay, that's correct. Now, why don't you think about what is 3/7? Now, in that case, if the remainder is 3, it's going to be 4. So you know that it's going to be starting from 4, 2, 8, 5, 7, and then up to 1, because the 4 is repeating. So let's try that. All right. I need to review. Let me see. Let's get everything. 4. And let's get 5. Let's get 6. All right. Looks like I may have some bugs in this program. I need to refresh it. All right. So if you are a programmer, you may understand what's going on here. All right. I need to refresh the page. So there is one-to-one correspondence with the remainder and the sequence, and the sequence in the results. Okay, so as you see, if it's 1, we're going to start with 1, 1, 4, 2, 8, 5, 7. If we're going to start with 6, the remainder 6, the next one will be 8. So which means the number is 8, 5, 7, 1, 4. So this is kind of a cyclic pattern. All right. So what about the reverse? Like every repeating or terminating decimal, is that a rational number? The answer is yes. All right. So in other words, any such decimal is actually a fraction number of two integers. All right, p over q. Now we're not going to prove that, but let's just revisit 1 over 7, right? So for example, if we're given a repeating decimal number, in this case happens to be 0.142857 repeating itself, we don't know what it is. Let's assume it is x. All right. So we take the fact that this is actually repeating sequence. So if you move the decimal to 6 digits to the right, what you get here is 10 to the 6 of x would equal to this integer value, right? This integer value plus this entity here. Now you notice that this entity happens to be x again. So you're going to rewrite this equation as 10 to the 6 x equal to this one plus x. Of course, you move over x to the left hand side, and this equation becomes 6 nines equal to this number, so which means x is a fraction number. Of course, we can reduce to the simple form because this happens to be 1/7 of 999999. All right. So in general, any repeating sequence, you can actually put the value into a algebra equation where the integer coefficient, and then if you solve the equation, and then you get the some fraction number with integer fractions. So that's a rational number. Of course, the irrational number is a number that there actually runs forever, but there's no repeating pattern. Okay, that's a key difference. Now, for example, there are a lot of irrational number. The most famous one would be pi or square root of 2. All right, so we're gonna skip the discussion on the irrational number. All right, so I think that's it for the talk on the fraction and repeating decimal representation of fractions. All right, so we're gonna show some other example before I say goodbye to you. One example, again, I'm gonna use my small program, but this time I'm gonna print out the remainder in each steps. For example, let's go 1 over 7 again. It's going to give us the value, but I just print out the corresponding remainder here. When you first one, this is the remainder values. All right. So let's try 19 here. All right. So 19 here, of course, the sequence is longer. In this case, it's actually 18. 19 minus 1. 18 of them, and just notice that the remainder has every number from 1 to 18. All right. So that's, and then later it's going to repeat this sequence. All right. So let's try another number, which is 31. All right. So notice that the sequence is actually shorter now. It's 15. And the interesting thing is that the remainder here, even though the possibility of the remainder is 1 to 30, but here we only have 15 of them. All right, so we're missing 1/2 of them. All right, so interesting thing is that if you put 3 here, you're going to choose the other half. Notice here, I have 1 here, I have 2, but I don't have 3, I don't have 4, I have 5, right? So if you do a 3 over 31, the sequence length is also, the repeating sequence is actually 15 length, and then you don't see 1, 2 here, but you do see 3 here, all right? So that's interesting. If you use learn like more advanced mathematics, like number theory and others, you can study that. All right. And then let's try another number. The pi is a irrational number, but sometimes people use a fraction to, uh, you know, have a approximation of pi, right? For example, in the very old days, people say, oh, maybe pi is roughly 22 over 7, right? In this case, it's actually repeating, but it's just a 3.1428, right? It's not a good approximation. And there's another one which is better approximation with 113. Again, this is a rational number. It's not really a pi, but it's just approximation of the pi, all right? So unfortunately, I may run into a bug where the value is not showing here, all right? Okay, so I think I give you another example here, which is 1 over, let me see, 81. All right, that's an interesting example here. All right, so the sequence here is actually is about 10 digits, I think. All right, you have 0, 1 to 9, right? But actually you are missing 8, right? So, and then this is 0, 1, 2, 3, 4, 5, 6, 7, and then missing 8, and then 9, all right? So that's it for today's talk, and hope you enjoy the video, and I welcome your comments. Thank you.